Alright, so today we're going to be going over computational methods homework 4 part 2, where we implement functions for calculating dew and bubble temperature for an equimolar mixture of methanol, ethanol, and water at atmospheric pressure. So first thing we have to do is we have to talk about what dew and bubble points are. So the bubble point is the temperature at a given pressure or the pressure at a given temperature where the first bubble of vapor is formed from a liquid. So that vapor will be all gas, and in multi-component mixtures, it will most likely have a different composition than the liquid, which we'll see towards the end of this video. And when there's only one component of a mixture, the bubble point and the dew point are both called just the boiling point. It only becomes important when we're talking about multi-component mixtures. Okay, and here's a graph showcasing basically a graph showing both the dew point and the bubble point. So here we can see that this is a two-component mixture where there's this bubble point curve and this dew point curve relating to the amount, the mole fraction component 1. Okay, so as we heat up, let's say we have about 0.4 fraction of liquid. As we heat it up, eventually we'll hit this bubble point curve, at which we'll get a bubble. Now that bubble that is formed is the exact same temperature as the liquid. So we follow this temperature along here, and this point here is the actual mole fraction component 1 in the vapor phase. So this is a good example of showcasing the difference between the bubble point and the dew point. And also, you'll notice that the bubble point and the dew point curve rest between the boiling points of pure component 1 and pure component 2. That'll be important later, because the dew point and the bubble point at any mixture will have to be between the highest boiling point and the lowest of any component in the mixture. Okay? So now, how do we actually go about solving for a bubble point? Well, first we're going to talk about Reupload's law. So if you remember in the last video, Reupload's law is the relationship between a component's partial pressure and its liquid phase mole fraction. So the idea is, for a single component, its partial pressure contribution is equal to its liquid molar fraction times its saturation pressure at equilibrium. Okay, so let's expand that out and talk about, well, what about the gas? What about the dew point? And this is where we get this. So this is expanding out the definition of a partial pressure, which is just the partial pressure equals the total pressure times the gas molar fraction. So we get this. So this is that Reupload's law expanded. And as we do and what we can do is we can actually add those two together for a two-component mixture and say, the total pressure, which is the sum of all these components, is equal to the sum of the liquid phase molar fractions times their saturation pressures. And you can see it here. So there's the bubble point equation. And the dew point equation looks kind of similar, actually. It's this. Except in this case, it's actually 1 over P equals this. Okay? So how do we actually implement them? So I have here a continuation of the previous homework, bubble point and dew point. So first thing we're going to need is we're actually going to want the same constants as from homework 1. So I want these 3. And our props is a Python class that we use to identify, we're going to use it to pull boiling points, vapor pressures, and other stuff for each of these methanol, ethanol, and water components. And the last thing we need is to define our pressure at 101,325 pascals. Okay, so let's make sure we got everything. Looks good. So let's jump into it. So first things first, in order to find the bubble point temperature at a given pressure, we first have to make a function about the bubble point pressure at a given temperature, and you'll see why in a minute. So let's start there. Let's start bubble P, and that's given a temperature and a liquid fraction, an array of liquid fractions for each component. And then the first thing we're going to want to do is we're going to code in, where's my equation? There it is. So we're going to code in what the equation we want is we want this one up here, which is wherever it went. I want this one. So if you remember, YA times P is equal to our partial pressure PI. So what we're going to do is we're going to solve for PI, because we know X sub A, and we can pull up our P star A. So it's going to be PI is equal to X times our P dot PVAP. Now, what PVAP is it's from that same props class. Inside that file, there is a collection of vapor pressures for different components at different temperatures, and the equations in order to solve for it. So by doing it this way, we're giving it a temperature, and it's giving us all the vapor pressures of all three components that we have. Okay. Now, what this doesn't show you with Raoult's law is that this is for an ideal mixture, or an ideal components. In the real life, that isn't how it always works. So what we do is we apply an activity coefficient, which we calculated in the previous part of the video. So let's multiply that by our, let's see, which one do we want to use? Let's use this one. So NRTL einsum. Let's give it X and T. Okay. So that should calculate our PI. So let's do big P, which is the sum of the pressures, is just equal to MP dot sum of all of the partial pressures. Okay. And then we'll return PI. Okay, so that's our, let's run this first, run that. Okay, so that's our function for bubble pressure. Now what about our bubble temperature, the thing we actually want to solve? So let's do bubble T, P and X. Now here's where it gets a little different, because what we want to do is we're actually going to nest another function, let's just call it EQ. And we're going to call our function we just made, so that's bubble P, T, and X. And we want the first one, so just the pressure. Why did I do that? So that nested function we're going to use in a root finder that we'll use in a second. So let's actually jump right into it. So we're going to use, so we're going to solve for t, and then we're actually going to use the Brent Q root finder function. And for Brent Q, we need a function, and then we need the inner and outer intervals. So the function's easy. It's that EQ that we just made a second ago. Now, what about the inner and outer intervals? Well, like I said before, the bubble and dew points, temperature-wise, fall between the highest boiling point component and the lowest boiling point component. So let's call in our boiling points, and let's give it a pressure. And let's do TB low, our lower one, is going to equal our NP.min of TB. And our TB high is equal to NP.max of TB. Okay, so that'll give us our low and our high. And then we can actually use that as our lower and upper bounds. So TB low, TB high. Okay, so now we're there. That gives us our temperature. Now, temperature isn't the only thing we want from this function, but we also want Y. We want the molar composition of the vapor inside the bubble. So that's going to be Y. And that's going to equal, if you remember from this equation, YA is equal to XA times P star over P. Well, we have P star right here. We have X, which is given. And now we have P, which is also given. So let's do X times P dot P vap at our temperature that we just calculated, divided by big P. Okay. And we want to return T and Y. Okay. Well, let's check it. So that's called bubble T. And pressure, comma, X. Okay. So what this tells us is that our bubble temperature is at 347, which, well, let's see if that's reasonable. So let's print our TB. So let's print the boiling points of our three components. So our three components have a boiling point 337, 351, and 373, with 373 being water, which is just, well, water boils at 373 Kelvin at atmospheric pressure. That is known. So I would have expected our bubble point to be lower than that because methanol and ethanol are lower boiling point components than water is. So 347, that's good. That makes sense and that works. And we notice here with this array that also came that our methanol is the highest fraction of gas in that first bubble. It's almost half. And then you got some ethanol and a lot less water. And that should make sense too, because since methanol is the lowest boiling component in the mixture, it would make sense that it represents the most of any of the others. Okay, so that bubble point code makes sense. So now let's look at the dew point. So the dew point is a bit, it's different because, well, it's a bit more complicated to calculate. So we're going to focus on the ideal case because the ideal case is easier and makes a little bit more sense. So where do we start from here? So first we define our ideal function, our ideal dew point pressure given a temperature, because that one's easier to solve. And we're also going to give it a y, which is the molar fraction of gas. Okay. So let's start by getting our variable p vapor, which is equal to our p dot pvap at our temperature, which is the same one we used up here. So p dot pvap. Then to get our total pressure, we're going to use we're going to go back to, let's see. We're actually going to go back to these guys. So the way that we're going to solve that is it's going to be equal to 1 over mp dot sum y divided by our pvap. Okay. So by using that equation that way, solving for p, and we get all the sums of the, excuse me, that should be y. Our saturation pressures and our molar fraction of gas, we can get our total pressure. And then we can get our x by going back to our original equation, which is this one here. Because now we have p star, and we have y. So solving for x is relatively straightforward. So it's just equal to y times p divided by our p star. Okay? And then we're just going to return p and x. All right, so that's our dew point pressure with ideal conditions. Now we want to define our dew ideal temperature given a pressure and a vapor composition. So let's look at this. So what we want to do is we actually want to do something very similar to what we did with this bubble. And so much so that let's just copy and paste it. Okay. So we can probably get rid of this print command. And then we'll have to change this to dew ideal pressure. Change this to a y. So what else do we need to change? So now we need to rewrite this equation to make this x, make this y times p divided by p dot pvap of t. Okay, so that ran just fine. Now let's test it. Let's give it p, and for this one, we're going to give its vapor, we're going to make its vapor components equal to, let's make its vapor molar components equal to 1/3 of across. So it's equal molar vapor. PVAP is not defined. That's because I capitalized it. Simple typo. I've been known to make those plenty of times. Alright. That's because I forgot to return x instead of y. Let's run this again. Alright. So let's move this down. So you can see now, side by side compare, we have our bubble temperature and our dew temperature. So our bubble temperature is about 347 and our dew temperature is about 358. So what does that tell us? First and foremost, the dew temperature is supposed to be higher than the bubble temperature at any pressure. At a given pressure, I should say. At a given pressure. That's good. And if you'll notice, the composition of methanol, which I highlighted earlier as being the highest in the bubble, at the bubble point, is the lowest at the dew point in the liquid form. So, as a reminder, the dew point is that temperature and pressure when the vapor condenses into a liquid. So in that first drop of liquid, there is a lot less methanol than there is in the gas, and correspondingly a lot of water than there is in the ambient gas. So it's over half water, actually. Whereas in the bubble, there's only a little bit of water, like an eighth. So that just goes to show how to calculate dew and bubble temperatures using those activity coefficients that we highlighted earlier. Hold on. I completely forgot to include those activity coefficients, so thank you for reminding me. But that should be here times. Then we want to throw in our NRTL einsum, y, and t. And let's see how much that changes our answer. Let's just see how much that changed your answer. So remember, so it calculated at 358.1, and it's slightly changed. Looks like it's slightly changed these fractions, but didn't really appreciably change this. So, you know, applying those activity coefficients, our activity coefficients as shown up in the previous section, they were 0.9, 1.1, 1.6. They make changes, but the changes aren't massive. And for the most part, Rhodes' law, even though it's designed to work with ideal systems, if you can't have the activity coefficients, we can get an answer that's approximately correct. So join me in part 3 of this homework, where we can implement flash calculations to calculate vapor and liquid compositions of a flash strobe. So hope to see you there.